scientific process as a unifying thread to make connections in chemistry. In part 3 of this video series, we discussed in detail the first 4 tools of major activity 3 of the scientific process, namely making sense of, understanding, and hence explaining facts that are generalized into empirical classifications and laws, and those that still remain isolated. We also discussed the corresponding results. In this part, we will look in detail into the remaining 4 tools of this major activity and the corresponding results. As the fifth tool of major activity 3, one uses deductive logic to derive from the postulates of a relevant theory the already known relevant facts and thus explain them. That is, the objective is to answer the following question. If the invisible, unobservable aspects of nature are what the postulates assume them to be, why or how should the known facts in the visible, observable world be the way they are? While doing so, it is important to indicate according to which postulate the given conclusion has been taken. Let us look at 2 examples of such an elegant explanation by a theory. Notice that wherever needed, we make a reference to the corresponding postulate. First, we will consider the explanation of the law of constant composition of Daltonites discussed in part 2 by atomic theory. Recall the postulates of this theory listed in part 3 of this video series. The postulate number indicated here refers to the corresponding postulate listed there. According to postulate 1, the hydrogen element is made up of hydrogen atoms and the oxygen element of oxygen atoms. As we will soon see, since it is the logical analysis that we are discussing here that led to our ability today to talk about the relative masses of atoms, and since during the initial stage of Dalton's analysis the mass of one atom of any element was unknown, let us assume that the unknown mass of one hydrogen atom is x gram and that of one oxygen atom y gram. According to postulate 2, x has the same value for all hydrogen atoms and so does y for all oxygen atoms. Also, according to postulate 2, x and y represent 2 different values. As per postulate 3, hydrogen atoms and oxygen atoms combine in a specific whole number ratio to produce the molecules of water. Although Dalton assumed the simplest possible ratio of 1 to 1 for the combining ratio of hydrogen and oxygen atoms, today it is believed that thanks to Avogadro's theory and its elegant explanation of the Gay-Lussac's law of gaseous volumes, this ratio is 2 to H2O. Hence, the formula of water is H2O. Therefore, to form one molecule of water, X plus X equal to 2X gram hydrogen and Y gram oxygen should combine. Here, notice that it is postulate 2 that allows the above addition of two X's to obtain the masses of two hydrogen atoms as 2X gram, since it assumes the mass of one atom of an element to be the same as that of any other atom. If they were different, we would have to know both values before adding them, which would make our approach more complicated. This is the reason behind Dalton's assumption. Thus, the ratio of the combining masses is 2x to y. To form two molecules, this ratio is 4x to 2y, which simplifies to 2x to y. To form 100 molecules, this ratio is 200x to 100y, which also simplifies to 2x to y. In the generic case of forming n molecules of water, this ratio turns out to be 2nx to ny, which also simplifies to 2x to y. Thus, all combining mass ratios are equal to one another and hence form a proportion. That is, all samples of water have the same composition of hydrogen and oxygen by mass. An exactly similar deductive logic is applicable to any other Daltonide. Hence, the law of constant composition of Daltonides. The above explanation by atomic theory makes it clear as to why the behavior of elements forming Daltonides is controlled by the law of constant composition. There is a remarkable consequence of the above deductive logic. The theoretical ratio of combining masses of oxygen and hydrogen equal to y gram to 2x gram at the microscopic level must obviously be equal to any experimental ratio at the macroscopic level. For example, let us consider the experimentally known ratio of 16.00 gram O2 to 2.016 gram H2. This leads to the result that the mass of one oxygen atom must be 15.87 times the mass of one hydrogen atom as shown here. Although we cannot measure the masses of the invisible atoms, the theory is able to shed light on their relative masses. That is, how the mass of one atom of one element compares with that of another element. That is indeed the power of a theory. Theories show us the mathematical relationships between experimental data at the macroscopic level and the properties of particles at the microscopic level. Using those equations and the corresponding experimental data, we are able to calculate the values of those properties. One may wonder if atoms, molecules, etc. are invisible. How come we are able to talk about atomic sizes, bond lengths, bond angles, angles, ionization energies, and so many others. One should always keep in mind that it is theories that have allowed us to talk in terms of the numerical values for the above properties. Dalton arbitrarily assumed the mass of one hydrogen atom to be exactly 1. Given this standard, he called the relative masses of other atoms as their atomic weights. The correct term is atomic mass, given our understanding of the difference between mass and weight. Since he assumed the combining ratio of the numbers of atoms of hydrogen and oxygen to be 1:1 to produce a molecule of water, he obtained a wrong value for the atomic mass of oxygen. Using the correct ratio of 2:1, the atomic mass of oxygen is as obtained above 15.87 as per Dalton's standard, namely atomic mass of hydrogen is exactly 1. Dalton assigned no unit for atomic mass. As mentioned in part 2 of this video series, while discussing the law of constant composition, Berzelius, an avid experimental chemist known in Sweden as the father of chemistry, synthesized a large number of compounds and published a table of constant composition of nearly 2000 compounds in 1818. The motivating force for this came from his strong belief in atomic hypothesis and a deep desire to determine the atomic masses of elements. During this task, he found it convenient to use the very reactive oxygen as the standard and assumed its atomic mass to be exactly 100. The standard for atomic mass was later changed by chemists to exactly 16 AMU for the average mass of the oxygen isotopes and by physicists to exactly 16 AMU for the mass of O16 isotope. AMU is the acronym for Atomic Mass Unit. As the two standards differed slightly, it created unnecessary confusion during very precise calculations. Finally, in 1961, the current standard of C12 having a mass of exactly 12U was adopted by the International Unions of Pure and Applied Chemists and Physicists, namely IUPAC and IUPAP. Several textbooks wrongly use the former unit of AMU even today. The correct unit presently used is U, which stands for Unified Atomic Mass Unit, that unifies chemists and physicists with respect to the standard for atomic mass. The unit is supposed to indicate the corresponding standard used. The values of atomic masses found in the periodic table of elements are on the basis of C12 as the standard, and hence the correct unit to be attached to these values is U, not AMU, although the values are not different when we use just 4 significant figures. One may validly wonder about the applicability of postulate 2 of atomic theory given the existence in nature of isotopes of an element that have different masses. But it is still applicable when we use the average mass of the isotopes as the mass of each atom. One reason for this is the constant composition of the isotopes and therefore the average being a constant. The second reason is statistical. If we happen to deal with a small number of atoms, there would be no guarantee that the collection would have the same composition that we know of. However, in the macroscopic world, the number of atoms is very large, namely of the order of Avogadro's number. Given the law of large numbers in statistics, the collection should have the same known composition of isotopes and hence the average mass should work. The atomic masses given in the periodic table or the average masses of the isotopes calculated using the known constant composition of isotopes, and thus these can be used. The second explanation by atomic theory that we look at now is for the law of conservation of mass, again discussed in part 2. According to postulate 4, at the microscopic level, atoms can be neither created from nothing nor destroyed into nothing, but are only rearranged during any chemical reaction. That is, the only change that occurs is which kinds of atoms are bonded to which other kinds of atoms when reactants get converted to products. Therefore, the total masses at the macroscopic level cannot change during a chemical reaction, since those masses are nothing but the total of the masses of the atoms participating in the reaction. Hence, the law of conservation of mass. It is evident from the above explanation why the reactants and products of all chemical reactions are controlled by the law of conservation of mass. For the elegant explanations of the relevant facts offered by all theories in chemistry, see my book, Understanding Chemistry. Whenever a student comes across in a quiz or exam any question that contains the interrogative adverb why or how, it is important to identify the particular theory that is concerned with the context of the question and use a postulate or postulates of that theory to offer the explanation. Keep in mind that we always seek an aspect of the invisible, unobservable, microscopic world to explain what we observe in the visible, observable, macroscopic world. Although a theory, by definition, has been very successful so far with respect to its explanatory power, it does not imply that it is the final say. Therefore, the sixth tool employed in major activity 3 is to subject even a theory to tool 2 discussed in part 3 by by resorting to a thought experiment, predicting the expected result, and verifying the prediction. After the thought experiment is performed and the result obtained, tool 3 is resorted to. That is, if the prediction by the theory does not agree with the experimental result, an attempt is made to either modify any suitable postulates, or if it fails, completely change the direction and replace all the postulates with a new set of postulates that can explain the old as well as the new facts. Whether the old theory gets supported or a modified or new theory gets framed, it continues to be subjected to tools 2 and 3 repeatedly. That is, we try to predict more unknown facts and perform experiments to verify the prediction. On the other hand, if the prediction by the theory agrees with the experimental result, we retain it and continue to subject it to tools 2 and 3. And this back and forth interaction and interplay between facts and postulates continue forever, making science an extremely fascinating one. As mentioned in part 3, since chemistry abounds in theories, it is no doubt a fascinating branch of science. Next, we will see examples for both situations, namely thought experiments refuting as well as supporting theories. After Heisenberg stated his uncertainty principle as a consequence of the wave-particle duality idea of de Broglie theory, it became evident that either Bohr theory with its idea of determinism, due to its ability to calculate both the radius of an orbit and hence the position of the electron in it, as well as the momentum of the electron at the same time, should be correct, or de Broglie theory with its idea of indeterminism due to the uncertainty principle has to be correct. Both cannot be valid at the same time, only one or the other. Schrödinger used de Broglie theory and came up with his equation to describe electrons' dual behavior as wave and particle. Both theories' limitations and failures to explain certain facts were recognized. On the other hand, the ability of Schrödinger's quantum theory to explain those facts was realized. Hence, Bohr theory's idea of electron orbits and determinism was dumped and replaced by the orbital idea of quantum theory. But Bohr theory's idea of quantization was retained in quantum theory. Although dumped, Bohr theory is often included in textbooks due to its simplicity in introducing the idea of quantization. However, it should be kept in mind that a serious limitation of Bohr theory is its applicability to only one electron species, such as the hydrogen atom and He plus, Li2 plus, etc. ions. It is completely wrong to mix the results of quantum theory with those of Bohr theory and teach students that Bohr's first orbit can hold two electrons the second orbit 8 electrons and so on by using quantum theory's results, namely the first shell can hold 2 electrons, second shell 8 electrons, etc. Bohr theory could not obtain such results of quantum theory as it could not successfully treat more than 1 electron in an atomic species. Since chemical affinity theory and caloric theory failed in their sole function of explaining and predicting facts, both of these were replaced by thermodynamic theory. In contrast, let us consider the following example of a thought experiment supporting a theory. In 1900, Planck sowed the seed for the birth of modern quantum theory through his theory of black body radiation, in which he postulated quantization of energy to solve the first mystery of that time. Einstein watered it in 1905 through his theory of photoelectric effect to solve the second mystery and contributed to its further growth by Bohr in 1913 through his theory of atomic emission to solve the third mystery. Using this old quantum theory, Einstein also solved the fourth and last mystery, namely low temperature heat capacities. After a couple other developments, namely de Broglie theory that postulated wave-particle duality in 1924 for matter also, like Einstein did for radiation in his photoelectric effect theory, and the consequent Heisenberg uncertainty principle, Schrödinger postulated modern quantum theory in 1925. However, Einstein later did not like the probability idea at all, which turns out to be at the core of modern quantum theory after Max Born gave such an interpretation for wave function postulated by Schrödinger. He hated quantum theory until his last breath, in spite of his contributions to its growth. During a debate between him and Bohr, he said, "I am at any rate convinced that God does not play dice, implying that God is not involved in gambling where probability plays an important role." Bohr quipped, "Einstein, stop telling God what to do." But yet, in order to refute quantum theory, Einstein imagined the EPR thought experiment in 1930 along with his co-workers Podolsky and Rosen. Using quantum theory, he predicted what he considered to be the weird result of this experiment and expected the actual result to be different from his prediction. That is, he expected the EPR experiment to refute quantum theory and cause its death. The then technology didn't permit the EPR experiment to be performed. 50 years later, it was carried out after the development of suitable technology. In contrast to Einstein's expectation, the result agreed with the prediction and contributed to the further growth of quantum theory. Today, it is considered to be an extremely powerful theory as it helps us make sense of an enormous number of facts, including what are considered weird facts regarding the microscopic world of particles. They appear weird simply because they are just different from our own experience in the macroscopic world. Thus, the above is an example for thought experiments supporting theories which are then retained. Textbooks include only theories, not hypotheses, except for historical reasons or for the sake of continuity, since they get modified, dumped, or elevated to the status of theories. J.J. Thomson's plum pudding hypothesis is included in some textbooks, and theories such as caloric theory that were dumped at one point are not normally included except when the history of evolution of ideas is emphasized. The seventh tool used in major activity 3 is to analyze the postulates of theories and recognize classifications in the microscopic world of particles that parallel the empirical classifications in the macroscopic world of substances. The corresponding result is theoretical classifications. A popular example is the theoretical classification of matter particles, which in my opinion may be referred to as matricles, into atoms and molecules thanks to atomic theory, as well as into formula units made up of cations and anions formed from atoms or groups of atoms thanks to Arrhenius theory. This theoretical classification parallels the empirical classification of substances into elements and compounds in the macroscopic world. The eighth and last tool used in major activity 3 of the scientific process is to analyze the postulates of theories and recognize the existence of rules followed by nature in its behaviors. Such rules are referred to as the principles of nature. These should be contrasted with laws, which are also rules but recognized through the analysis of experimental data. Laws are the result of major activity 2A, but principles are the result of major activity 3. Some examples of principles and the corresponding theories that helped the recognition of these principles are listed here. Peter Atkins, in his physical chemistry textbook, correctly refers to Avogadro's principle with that name on page 7 of the 11th edition, whereas many others wrongly call it Avogadro's law. Although principles are also rules, it is advisable to replace the term rule by principle in cases like Gibbs rule and Hunt's rule, especially since laws are also rules. And in addition, as we will see in part 5, there are also simple rules such as cyclic rules and crisscross rule that serve as major learning aids. It is important to clearly keep the distinction in mind, and using the term principle for Gibbs principle and Hund's principle helps this. The whole collection of theories, namely their postulates about the invisible, unobservable, microscopic world, theoretical classifications, and principles, constitutes the second of the two major types of scientific knowledge called theoretical knowledge. Recall from part 1 of this video series that the facts observed, either isolated or generalized in the form of empirical classifications and laws, constitute the first major type of scientific knowledge called empirical knowledge. The theoretical explanations of facts using theories, as illustrated earlier with two examples using atomic theory, form the bridge between these two major types of scientific knowledge. Another widely prevalent misconception regarding scientific method is that a theory is elevated into a law. Recall the opposite nature of the tools used to arrive at both of these. That is, experimental observations on nature serve as the origin of laws, whereas human speculations about nature serve as the origin of theories. No theory changed into the law of constant composition of compounds or the law of conservation of mass. What about atomic theory? Did it? No. It was invoked to make sense of their existence in nature. No theory changed into the first and second laws of thermo. What about thermodynamic theory? Did it? No. It was framed to understand their existence in nature by postulating internal energy U and entropy S respectively. No theory in chemistry ever changed into any law. A hypothesis is elevated into a theory but not a theory into a law. Let us say that one fine day we obtain the special power to be able to directly see the microscopic world of particles that we have postulated to exist. From that day onward, atoms, molecules, electrons, protons, etc. would all become facts, just like the elements and compounds that they make up. Principles could turn into laws, but in the absence of such a special power, theories will continue to be theories, not elevated into laws. This confusion between law and hypothesis or theory exists even among several physicists. For example, a quote by Feynman from page 156 of The Character of Physical Law is in order here. Let us read this quote by replacing the term law by hypothesis and making a few other suitable minor changes. Always we frame a new hypothesis, not law as Feynman put it, by the following process. First, we guess it. Then we logically deduce the consequences of the guess to see what would be implied if this hypothesis that we guessed is right. Then we compare the result to nature with experiment or experience, compare it directly with observation to see if it works. If it disagrees with the experiment, it is wrong. In that simple statement is the key to science. It doesn't make any difference how beautiful your guess is. It does not make any difference how smart you are, who made the guess, or what his name is. If it disagrees with the experiment, it is wrong. As illustrated above, the wrong statements by Feynman become correct by a simple substitution of the term law by hypothesis. Guessing plays no role at all in the case of a law. Instead, a suitable analysis of the experimental data reveals its existence to us as indicated in Major Activity 2A, discussed in detail in Part 2. But guessing is an essential tool used for framing a hypothesis as indicated in Major Activity 3 with the sole intention of making sense of, understanding, and hence explaining facts which may then be elevated to the status of theory. Another widely prevalent misconception has to do with mixing up the name of a theory with the name of the branch of science which includes that theory. One very common example is the confusion between quantum mechanics and quantum theory. When the context demands the use of the term quantum theory, the term quantum mechanics is often used. The latter refers to a large collection of both empirical knowledge and theoretical knowledge. At the heart of that theoretical knowledge is quantum theory, postulated by Schrödinger in 1925 with a view to making sense of that empirical knowledge. Thus, quantum theory is only a specific part of quantum mechanics. It is obviously wrong to use quantum mechanics to refer to quantum theory. In Part 5, we will discuss the fourth and last major activity of the process of science, as well as 4 major learning aids that facilitate the student's learning process.